All right, so we're here. We're wrapping up our chapter on alkynes. Again, chapter 9 in the third edition book, chapter 10 in the second edition book. And we just have a couple of reactions here to wrap up. And then once we're done with that, we have just a brief section on synthetic strategies that we can use when we do multi-step synthesis problems. And when we take a look at those, kind of integrating them into the broader picture of organic chemistry that we know so far and that we're going to learn in the next semester as well. So, okay, so right, wrapping up the reactions, we're starting with ozonolysis. So you may remember ozonolysis, basically for an alkene is one that you take your alkene, you react it with ozone, and then in a second step you add water, and you form a set of basically carbonyls that come from that. Now the same reaction or a similar reaction occurs with alkynes, where you take your alkyne, react it with ozone, and then protonate everything after that ozone has kind of ripped through that alkyne. What actually happens is the two carbons, the alkynyl carbons, are going to become carboxylic acids. So this is an easy one to do because if you don't have to know the mechanism, you don't have to worry too much about kind of the details about how the ozone works its way around. Basically, what you do is you just take these carbon-carbon triple bonds and say, okay, this is my one compound. I know that this carbon is going to be a carboxylic acid. Okay, and then I know this carbon also going to be a carboxylic acid. So it's really easy to draw out what the products are going to look like. It just looks like these here. You just kind of like rip it apart. And that's kind of what the ozone do. It like chews it up. So that's that. Now, one thing that is different is if you have a terminal alkyne, the terminal thing here, it would form formic acid, but formic acid isn't stable in the presence of ozone. So it actually forms carbon dioxide. So just keep that in mind that like, as you do this, if you have a terminal alkyne here, this part is going to become the CO2. This part becomes the same carboxylic acid. You don't have to worry about that. Okay, so go ahead, give it a shot. Try to predict what the products of this one are going to be. You can write it on your paper. I recommend pausing the recording. And then once we come back, you can check your answer. So go ahead, pause the recording. Okay, and let's go ahead and check our answers here. Here in this case, because we have a symmetrical alkyne, we have cyclopentyl on either side. That means that when we chew it up, we're going to end up with two carboxylic acids that are the same. So this carbon here becomes a carboxylic acid. This one here becomes a carboxylic acid. And that forms our products. Yeah, so this can be very useful if we're forming carboxylic acids as a product, because if we start with the symmetrical alkyne, then we end up with this two equivalents of our carboxylic acid. We're not wasting any of the carbons. Okay, and near basically like one of the most important reactions we're going to leave for the end. So remember at the beginning of the chapter, we talked about how a terminal alkyne can be deprotonated and you form this alkynide ion. Now this alkynide ion becomes a really good nucleophile. And what's important about that is a good nucleophile can be used in SN2 reactions. So this alkynide ion, all of a sudden, you can form new carbon-carbon bonds just by doing SN2 chemistry with with any alkyl halide. And now that is the big deal. So like forming a new carbon-carbon bond is one of the hardest things to do in organic chemistry because there's no way to pick apart carbon-carbon bonds that's like that doesn't involve kind of chewing up more of the compound than you want to. So being able to form a new carbon-carbon bond is going to invite all sorts of new kinds of chemistry, and this is how you can build up a carbon skeleton as you try to build bigger and more complex molecules. So yeah, so basically this is what we call alkylation. You take your terminal alkyne, you deprotonate it, form an alkynide ion, and then you use whatever SN2 reactant you want. This is ethyl iodide here. This ethyl iodide, basically iodine's a really good leaving group, and this is going to basically add a new two carbons on top of the alkyne. Now, if you start from acetylene, you can actually do this twice. You can do an alkylation on the left side, then do an alkylation on the right side. You can get different products based on that. So that can be useful as well. And then yeah, keep in mind, like you're going to do this stepwise. So you do the NaNH2, that gives you your first acetylide, then subject it to the SN2 reagent, that's your ethyl. And then you can just do it again. You subject it again to the sodium amide, and then use, in this case, we could use methyl iodide. Well, that's going to put a methyl group on the other side. So yeah, so this is a one really cool way that you can make more complex skeletons, is by building it up using this alkylation of alkynes reaction. Okay, so those are the last couple reactions. Now let's go ahead and try to like contextualize everything. Remember, alkynes can be converted to alkenes using either H2 and a poisoned catalyst like Lindlar's catalyst, or metal reduction, which is sodium in ammonia. So that gives you the alkene. Remember, this is the transalkene down here. This is the cisalkene that you form up here. You can also go from an alkyne directly to an alkane using hydrogenation. So platinum catalyzed hydrogenation, hydrogen on platinum. And of course, you can take an alkene to an alkane using the same process, hydrogen on platinum. Yeah, so, but what if, so that's easy enough to do, right? You can go alkyne to alkene, no problem. What if you wanted to go the other way? Go from an alkane to an alkyne, let's say. So the way that you can do that is if you, for example, let's say that we have an alkene, you can halogenate it. When you halogenate it, you get a dihalide, a vicinal dihalide. Now this vicinal dihalide can be subject to elimination. So use a strong base like sodium amide again. I know I keep saying that, but that's very convenient strong base. You do the first elimination, that gives you your haloalkene, but then you can just do a second elimination, and that would give you the alkyne. This is an easy way to get from alkene to alkyne. And so this is a way that we can basically interconvert single, double, and triple bonds. Now, the way that you can do it down here, so this is C chapter 10. This was something that we covered when we talked about radical reactions before. Remember, you can brominate an alkane, and then once you brominate an alkane, you can do an elimination reaction, and then once you eliminate it, you can get your double bond there. So that's something that you're going to want to practice with more and more, and we'll make sure to have more practice problems in the notes down below. So yeah, so here's our reactions that you can all do. Remember, elimination to produce alkynes. Basically, di-elimination reactions occur. Hydrohalogenation can do 2 or 1 equivalent of those. We have acid catalyzed hydration, which forms the Markovnikov product, the enol, which becomes the ketone. And then we have hydroboration oxidation, that's anti-Markovnikov enol, which becomes the aldehyde, or it could be a ketone as well. Halogenation with 1 equivalent gives you your dihalogenated alkene. If you do it with 2 equivalents, you get your tetrahalogenated alkane. Ozonolysis, that's where you produce 2, you basically split the alkyne in half and you produce your 2 carboxylic acids. Alkylation, that's what we just talked about with the terminal alkynes participating in SN2 chemistry. We have dissolving metal reduction, hydrogenation, and hydrogenation with a poison catalyst. Where again, dissolving metal reduction, that's where you take sodium in NH3, and that produces the trans alkene from the alkyne. Hydrogenation, that's platinum on hydrogen, produces the alkane. Hydrogenation with a poison catalyst gives you the cis alkene. So yeah, this is kind of the whole chart that we have here, kind of starting from the beginning. Get some practice, try to work with this chart. We have some more practice problems down below. I'll make sure to be checking in on your homework progress as well. Send me any questions that you have in the comments below. I'm happy to answer anything that you are curious about. But that does it for alkynes. So for the end of the semester, we've just got one, it's not even really a chapter, it's just like how to work through longer synthesis problems. So it's like, I think we have like one more video, or maybe 2, I think 2 videos left in the semester, but they're very short. So we're going to record those, and I will see you very soon. Let me know if you have any questions. Bye-bye.